Welcome to this explainer. Today, we've got a seriously fascinating dual focus. We're going to unpack the actual on-the-ground science of nuclear fission, and we're doing it right through the lens of a massive real-world megaproject, Bangladesh's historic Rooppur Nuclear Power Plant. 10 to 12%. Just pause and think about that number for a second. That is the staggering amount of Bangladesh's entire electricity demand that this single nuclear project is expected to meet once it's totally up and running. I mean, it's a massive leap for the country's energy grid. It's going to completely shift how millions of people get their daily power. Now, this milestone, it has been a seriously long time coming. The project was actually conceived way back in 1961. Yeah, 1961. It took all the way until 2011 for a major agreement to finally be signed with Russia. Then, the first uranium fuel arrived in 2023. Fast forward again to April 28, 2026, when fuel loading officially kicked off, pushing the plant right into its active commissioning phase. And by early 2027, that first unit is expected to hit its full 1,200 megawatt output. Okay, here's our roadmap for today. We're looking at the nuclear age begins, inside the reactor core, from steam to electricity, keeping the core safe, managing the waste, and finally, powering the future. Let's get right into it. Part 1. The nuclear age begins. Bangladesh's first plant. So, right on the banks of the mighty Padma River sits the Rooppur Nuclear Power Plant. And guys, the scale of this thing in Padma is just staggering. We're talking about a $12.65 billion mega project using these ultra-advanced VVER-1200 reactors. As of April 2026, with the nuclear fuel loading process beginning, this immense facility officially graduated. It went from being a massive construction site right into its highly anticipated commissioning phase. Moving on to Part 2, inside the reactor core, the microjourney. To really grasp how this plant works, we got to start with the nuclear fission itself. We're zooming all the way down from that giant concrete dome right down to the atomic level. Simply put, fission is just the process of splitting uranium atoms inside a tightly controlled reactor vessel. When those incredibly tiny atoms split apart, they release an absolutely immense amount of energy in the form of heat. Really, despite all the crazy complex engineering you see, at its heart, a nuclear reactor is basically just a highly advanced, incredibly efficient way to generate massive, continuous amounts of heat. Now, how they package this raw nuclear material is honestly fascinating engineering. It starts incredibly small, with these little uranium oxide pellets, literally just 8 to 15 millimeters wide, basically the size of a fingertip. These tiny pellets are stacked precisely inside metal fuel rods that are about 4 meters long. Next, you take 312 of these rods and bundle them securely together into what's called a fuel assembly. Finally, 163 of these massive assemblies are loaded directly into the core of the Rooppur reactor. That meticulously arranged geometry, that is exactly where the fission magic happens. Part 3. From steam to electricity. How it works. The actual process of getting power out of all this is beautifully logical. First up, that fission reaction we just talked about happens inside the bundled fuel rods, and that creates an intense amount of heat. Second, this heat is used to boil water, creating highly pressurized steam. Seriously, think of a giant high-tech tea kettle boiling on a stove. Third, that super high-pressure steam is blasted directly at massive turbines, forcing them to spin. It's essentially using steam to blow on a giant pinwheel. And fourth, as those turbines spin at incredible speeds, they drive a generator, converting that mechanical motion straight into the electricity that powers our homes. So to recap, heat creates steam, the steam causes the spin, and the spin generates the electricity. Part 4. Keeping the core safe, VVER-1200 technology. The Rooppur plant uses a modern Generation 3+ reactor design, which means it relies on 2 distinct layers of safety. First, you have your active safety systems. These are your traditional safeguards, stuff that requires external electrical power, motor-driven pumps, and active digital controls. But the true modern innovation here lies in the passive safety systems. These are brilliant because they rely entirely on natural, unbreakable physical forces. We're talking gravity, natural circulation, and compressed gas. They don't need a single drop of AC electricity to work if the plant somehow loses power. A totally brilliant example of this is the Passive Heat Removal System, or PHRS. Let's say the plant somehow loses all power. Well, this system just automatically kicks in. It uses natural circulation and air-cooled heat exchangers located way up high in the structure to naturally siphon the hot steam away from the core. It cools it back down into liquid water using nothing but regular atmospheric air, and then sends it back to cool the reactor safely.
It literally functions indefinitely without a single human having to press a button.
The plant is actually loaded with these fascinating passive failsafes. Take hydroaccumulators, for example. If the pressure inside the reactor drops, these tanks naturally inject a boric acid solution directly into the core, which physically stops the nuclear reaction. Then you've got passive autocatalytic recombiners. These automatically remove explosive hydrogen gas from the air inside the containment building using a simple chemical reaction. And at the very bottom of the facility sits the core catcher. It does exactly what it sounds like. It's this massive receptacle specifically built to safely catch, contain, and cool molten core material in the absolute worst-case scenario of a meltdown. And all of these systems, they're housed inside a massive physical architecture. It's a double containment structure made with pre-stressed concrete. It's basically a giant dome within a dome. The inner dome is designed to keep all the pressure and radiation safely sealed inside. Meanwhile, the outer reinforced concrete dome is built to withstand massive external events, like earthquakes, extreme weather, or literally even an airplane crash. Part 5. Managing the waste, the fuel life cycle. Okay, so the core is incredibly well protected, but what about the byproducts, right? Once those fuel assemblies are loaded into the core, they stay there for quite a while. Actually, a single fuel cycle inside the Rooppur reactor core lasts for approximately 18 months. That is a solid year and a half of generating absolutely immense heat continuously before the uranium fuel rods finally become depleted and need to be carefully removed and replaced. But the crucial point here is what happens next. Under a strict bilateral agreement, the spent nuclear fuel, which, yes, remains highly radioactive, will be returned to Russia under incredibly strict security arrangements. So Bangladesh doesn't actually have to figure out how to permanently store this highly radioactive waste locally. Instead, it gets shipped back to Russia, where it's managed and might even be reprocessed to be used in other fast breeder reactors. Finally, Part 6. Powering the future, economic and environmental impact. Stepping back out to the macro level for a minute, the environmental advantage here is just massive. If you compare it to a coal-fired power plant generating the exact same amount of electricity, the Rooppur plant is expected to save roughly 20 million tons of carbon dioxide emissions every single year. Let me say that again, 20 million tons. Even compared to a much cleaner burning gas plant, it still saves about 8 million tons of CO2 annually. It is an absolutely massive step forward for the region's air quality. And then there are the economics. $1 billion. According to experts from Dhaka University, commissioning just a single unit of this nuclear plant could save Bangladesh a staggering $1 billion annually in fossil fuel import costs. While the initial construction cost of a plant like this is undeniably high, the day-to-day fuel costs are remarkably low compared to importing millions of tons of coal or oil year after year. Which leaves us with a pretty provocative question. These modern reactors have a 60-year lifespan, which is actually extendable up to 90 years with proper maintenance, and they completely eliminate tens of millions of tons of carbon emissions. So with all we've learned today about how safe, passive, and incredibly efficient this technology has become, is nuclear fission the ultimate bridge to a clean energy future for developing nations worldwide? It's a fascinating thought to consider as energy demands continue to rise across the globe. Thanks for joining me for this explainer, and I encourage you to keep exploring the incredible science behind our energy grid.